Right. Let us move on to the ninth question. The ninth one. It's an argumental problem. You have to come up with a solution argumentally. Read the question. Ninth one means 1996. 1996. Right. So it says the diagram shows two boys pulling a bucket of water from a well. Which of the following graphs correctly represents the variation of the string capital T with the angle theta? Okay, with angle theta, which of the following best represents the variation of T? The tension. Right. Let me get this argumentally. Right. This is theta. This is theta. So if this was the bucket of water, the downward force, let's assume mg. If this is T, then this should also be T, right? Although it's two different strings, it is symmetric. It is perfectly symmetric. So therefore, you do not have to go with T1 and T2, right? So you can mark both as TT. It's perfectly symmetric, right? So actually, therefore, now we need to see how the tension varies when the theta angle varies, right? When this increases, when theta increases, we can't know, right? We can't come up with this answer argumentally. Argumentally, because like from common sense, if we try to go for the answer, sometimes we might make mistakes. So therefore, we can come up with the answer using a calculation as well, this kind of a problem, right? So first of all, let's assume, okay, equilibrium to this point. Let's assume equilibrium to this point, right? What is it then? Upward equilibrium. So that is udada thiyena forces මොකක්ද? T cos theta, T cos theta. 2T cos theta. What's the downward force? Mg. Downward force is mg, right? So if you see, T dot cos theta is equal to mg over 2. Now you need to understand that mg over 2 is a constant. mg over 2 is a constant. හරි? එතකොට මොකද්ද වෙන්නේ? T dot cos theta සමානයි T dot cos theta is equal to a constant K, something a constant, right? Now we need to get the variation of theta versus tension. Now let us see what happens when theta increases. When theta increases, what happens to the cos ratio? What happens to the cos theta? Increases or decreases?
Decreases, sir.
Decreases. Because you need to understand, when theta equals 0, cos 0 is 1. But when theta is equal to 90, cos 90 is 0, right? So when the angle increases, the cos ratio decreases. Cos ratio decreases. So when the angle increases, may cos ratio decreases. So when this term decreases, what should happen to the tension term? It should increase. Why? Because it needs to maintain the constant, right? Yeah. It needs to be constant. So when theta increases, tension increases as well. Now when theta increases, tension increases as well, right? So there's three curves, this, and once again this, and this. Actually, you need to come up with this answer, that is cos increases, like when theta increases, the cos value largely decreases. When theta increases, the cos value largely decreases, like 1 to 0. The maximum is 1, next 0, minimum is -1. So therefore, rather than this curve, this should be the curve which should work, right? So when theta increases, the cos theta largely decreases. So the tension, other side, sorry, I didn't mention it the other side. When theta largely increases, me cos theta ge aduwima podi ganak ne 1 to 0. Sorry, okay, other side.
Yeah.
When theta increases largely, there's a small decrease in the cos ratio. So when there is a small decrease in this thing, tension increases, small, like it increases, but the increase is less. The rate of increase is less. The rate of increase is less. So because the cost ratio rate of decrease is less, therefore the rate of increase is less. So this should be the answer. I don't know whether the Pesuru is wrong or this thing is wrong. What do you call the paper? Both the answers are the same. 1 and 5 are the same. If you check in the Pesuru also, they have given both 1 and 5. I did not check the 1996 paper. Somehow both 1 and 5
height is different.
Yeah, the first one there's a small height.
It starts from
height. Yeah. Initial, right? Initial. Somehow both the answers are given to be as like, I think we can't predict what happens. Just give me a second. What happens to the tension when what happens to the tension when the cos theta is 0? Cos theta binduvana, cos theta, like this is 1, this is 1. So there is a theta tension එකක් තියෙනවා. Tension is mg/2. දෙකේම mg/2 ගන්න පුළුවන් නේ. I mean, like if this first curve was given as this, it's wrong. The first curve was given as this, it is wrong, because when theta is equal to 0, cos 0 is 1, t is equal to mg/2. T වලට value එකක් තියෙනවා. It should be something mg/2. It should start from here, but both have started from this kind of a point. So therefore like both the answers are correct, right? So I think you can't predict it using the data given, whether it's first or the second. So therefore first or the fifth. So therefore both the answers are correct, right? So they have given as 1 and 5. All right, so is that understood? Let me move on. Let us go for maybe a question like okay, let us go for 16th question. 16th, 2001. Right. Okay. It says a uniform bar of mass capital M is suspended from its midpoint by a spring balance. Two masses M1, M2. M1 is greater than OK. A wedge supports the bar at the end capital B to keep it horizontal as shown in the figure. the reading of the spring balance is. They're asking the reading of the spring balance. So I think we will have to go for a diagram, right? So let us quickly mark the diagram. Right. Yes, sir. When you deal with equilibrium problems, draw contactless surfaces in order to distinctly identify the forces. Right. You need to find the force. You need to find the reading of the balance, right? You need to find the reading of the balance. So reading of the balance means the tension acting directly below it. So this is M1. M1 means it's going to have a weight M1G. So a reaction is going to be on this R. The reaction is going to be on this R1. R1. You see M2 means M2G. R2. R2 on the this thing. And then once again there is a contact surface here. So therefore another reaction R3 and on the wedge R3, right? So I think I have marked all the forces acting in the system. Does it have mass? Yes, it has a mass as well, capital M, and the string is connected to the midpoint, so therefore it should be here exactly mg. Right now they are asking us to find the reading capital R. They're asking us to find the reading capital R. So in order to find the reading capital R, we will have to find the tension T. So to
You
find,
take,
sorry,
can't we take moments?
sorry,
Moments
you're going to take moments.
can't, because it's fixed.
Yeah, you can take moments, but before that you need to see, like, okay, actually at the if you are solving this for the first time, you might think it's a very complex question, but there's nothing to do in this, right? So basic, one equation, you're going to get the answer. Let's see. You need to find tension, right? You need to find tension. So what you have to do is apply equilibrium to this system. Apply equilibrium. Okay, you need to find the tension, right? Mm, right. What if we apply equilibrium for this system? What if we apply equilibrium for this system? Things are going to be pretty easy. R1 to R1 cancels out. So okay, let us apply the upward equilibrium. Right?
R1 plus
R1
T.
no, R1 to R1 cancels out, right?
Yeah.
R1 upwards, this is downwards, so cancels out. So what
T.
are the other upward forces? T, right? T.
T. That's
This
all.
also cancels out. R3 to R3 cancels out.
Yeah.
R2 to R2 cancels out. There's no more other forces. What's the downward force? M1G.
M1G
Capital MG.
and M2G.
Simple M2G. So that is the only thing that supports this thing. So therefore, the answer is going to be, I have a small out on that. Let me 16th one. 16th one. That's not the answer, right? Because why? You can't. That's nice, right? That's nice. The thing is, you can't apply equilibrium for this system because you do not know the weight of this wedge. That's the problem, right? It's better that we encountered this, because now if they had given you the weight of this wedge, it would have been very easy. But now they have not given the weight of the wedge. So can we apply equilibrium, but can we consider this into the system? We will have to go from here, I guess. We'll have to go from here because we can't include this into the system because we do not know the mass. Have they mentioned the mass of no, a wedge supports the bar at the end B? That's only they have told, right? They have not told whether it's weightless or weight, so therefore we can't predict anything. So therefore that is this is incorrect. This method cannot be used. Right. Now let us go with this. So if we apply upward equilibrium, whatever R1 to R1 cancels out, upwards T1, sorry T, and R2 to R2 cancels out, but R3 is there. R3 to R3 cancel when we have include the system. So therefore this R3 to this R3 doesn't cancel out. So this R3 is there. That R3 is there, right? So is equal to what are the downward forces? M1 capital M simple M2 G, right? M1G capital MG simple M2G. All the others cancel. R1 to R1 cancels, R2 to R2 cancels, right? Why forces net. Now this R2 is not known. R2 is not known, right? So what we are going to do therefore is to find this R3, to find R3, we could maybe apply a moment around this point. Could apply a moment around this point. Right? Could apply a moment around this point. If we consider this end as end A, right? We're going to apply a moment around this point end A. If we apply moment around this end A, R1 doesn't come, R1 doesn't come, M1G doesn't come into the equation. Why? Because everything goes around this point where we take the moment. So therefore it's not going to be there. T1, T is there, T into, this is, let's assume this is length L and this is also length L. T into L, T into perpendicular L, that's anti-clockwise moment. Right? Anti-clockwise moment. What are the other anti-clockwise moments? R2 to R2 cancels out, so therefore no moment. M2G pahalata, R3 unata. So R3 into 2L. The moment is R3 into 2L. LL 2L. So is there any other moment in the anti-clockwise direction? T and R3. So the other clockwise moments, capital MG into L and M2G into 2L. So L cancels out. So T plus 2R3 is equal to Mg plus 2M2G. So R3 is Mg plus 2M2G minus T divided by 2 R3. You take this and substitute it here and simplify. Take this and substitute it here and simplify. You are going to get an answer for T. I think it's going to be the fourth one. Let us not waste time on the simplification. Let's only worry about the concepts, right? So once again, I will say what I did, right? So we could have taken the complete system, but the thing is we didn't know the mass of the wedge. So therefore, better we exclude the wedge when considering. So I considered this thing, excluding the mass of the wedge. So And then I applied first of all an equilibrium in the upward direction. R1, R2, sorry, R1 and R1 cancels out. R2 to R2 cancels out. T is upward and R3 is upward. So T, R3. What are the other downward forces? M1G, capital MG, M2G. Right. So, but the thing is, this R3, okay, if they are asking the mass of this mass shown in this scale, it is more than enough if we find the tension. But to find the tension acting directly below it, we need to find R3. But R3, how are we going to find? R3, and we will have to go for a moment. So, what I did was I applied the moment around this point. You can apply here also the moment, it's fine, but I thought of applying it here. So when I apply the moment here around A, you need to understand this R1, M1G is not going to come into the, it's not going to create a moment because they are going through the point which I take the moment around. So therefore, M1G, sorry, tension is going to create anti-clockwise moment and R3 is going to create anti-clockwise moment. So, okay. And M2G clockwise moment and capital MG clockwise moment. So therefore, and I subjected R3. Let us move on to the 2003 problem, 18th one. So the 18th question says, three masses A, B, and C are hanging from horizontal crossbars as shown in the figure. Each crossbar has negligible mass. If capital A has 6 kilograms, the masses of B and C are, okay, if capital B has 6 kilograms, we need to find the mass of B and C, right? Okay, so for this also, I think we would have to go through a diagram. Six kilogram means 60 newtons. So this is T1, T1, T2, T2, T3, T3, T4, T4. This is, let's assume, MBG, MCG, right? So we have to, they have also given the ratios of the distances. This is X, this is 3X, this is Y, this is 3Y. So one thing that we need to notice, here we can't apply equilibrium and solve the question. So we'll have to go through a moment, right? Moment question. Right? This is a moment problem. So A, if you apply equilibrium for A, you're going to get what? T1 is equal to 60. If you apply moment to B, it's going to be T3 is equal to MBG. If you apply moment to C, T4 is equal, sorry, moment, not moment, an equilibrium, MCG, right? So vertical equilibriums for all these objects, all right? So now I have found T1, T3, and T4, right? Now I'm going to apply moment around this joint, right? Let's assume this joint is O1. So around O1 joint, I'm going to apply a moment, right? So the T1 force creates a anti-clockwise moment. T1 force creates an anti-clockwise moment. Right? T1 into what is the perpendicular distance to the T1 force? It is X. So is there any other Anti-clockwise moments? No. Let's go for this side, T2. So T2 is going to create an anti-clockwise moment. Anti-clockwise moment. So therefore, if the system is in equilibrium, then the clockwise moments should be equal to the anti-clockwise moments, right? That's how it works, right? So if a system is in equilibrium, so around any point on the system, the clockwise moments should be equal to the anti-clockwise moments. So the clockwise moments is this, the anti-clockwise moment is T2 into 3x. X to x cancels, T1 is 60. T2 into 3, so T2 is 60 divided by 3 is 20 newtons, right? Okay, now next let us apply a moment to this joint, O2 joint. Let's go for the O2 joint. So around O2 joint, also the clockwise moment should be equal to the anti-clockwise moment because O2 point is also in equilibrium, right? So what is the clockwise moment? Clockwise moment is if you apply around O2, T2 is not going to come into the equation. T4 into 3y. So this is the clockwise moment. So with the anti-clockwise moment, T3 into y. But we know, but there's no T2. So 3T4 is equal to T3. But how can we relate this and this? Let's move it. What I'm going to use is, I'm going to apply equilibrium for this rod. I'm going to apply equilibrium for this rod. I'm going to apply a vertical equilibrium for the rod. So what is the upward force acting on the rod? T2, right? It is T2. What is the downward force acting on the rod? T3 and T4. So T3 plus T4. So T2 is what? 20. T3 plus T4. So we know that T3 is what? We know that T3 is 3T4. 3T4 plus T4. So 4T4 is equal to 20. T4 is equal to 5 newtons. T4 is equal to 5 newtons. But T4 is equal to 5. MC, G is 10. So MC mass is 0.5 kilograms. MC mass is 0.5 kilograms. So we know if T4 is 5, if T4 is 5, then T3 is what? 3 times T4. 3 times 5, 15. So we know T3 is 15. Then MB into 10, G is 10. So MB is 1.5 kilograms. Although we have done a lot of things here, like I can't, do a lot of mental maths because when I teach, of course, I have to teach everything. Like I have to teach each and every step. Right?
Yeah.
But when you do that, you shouldn't go and do like all these stuff on the workout, right? So as much as possible, because these are MCQs, so do not waste a lot of time. So as soon as possible, if you can work these things out in your head and the simplifications and all, if you can work it out, mental maths, do mental maths, please do that, right? Because time is very important. You get only 2 minutes for solving a question, so you can't do all these things, draw and mark all these things. In the bar, right? So මෙයාවට moment tag දැම්මා. I got an equation. Around this I did apply moment. Another equation. And I applied a vertical equilibrium. Another equation. I used all these 3 equations and got the answers for right fine. Okay, right. If that is okay, let us move on to maybe 2006, 21, 2006 to 21. Capital M is placed so that it touches a step at height capital R, as shown in the figure. The minimum value of the horizontal force capital F required to pull the coin over the step. Right. Here, you see there is a coin, right? There is a coin, and right, radius is R. Okay, but that's going to be it's going to have a weight acting at the center, capital Mg, and they're asking what's the minimum force that needs to be applied, right? This is R as well. This is R. So what is the minimum force that needs to be applied in order to lift this up? So it's kind of a problem. I think okay, there was some other year also, I can't remember, but yeah, okay, fine. Like, what do you think is like, what kind of a procedure are you going to, follow in order to solve this kind of a problem? If you get this kind of a problem, but would you do? Can you suggest me something? Like, apply this around this, or else, simply you have to find the minimum. It is going to come around which point? May point what is in the carriage. Like this coin is going to rotate around this point. Around this point. Let us assume this point is point 2. Right? Point 2. Now when it just starts to come up, it's going to lose contact here. Right? When it just starts to shift, it's going to lose contact here. No reaction. Right? They have asked the minimum value of the horizontal force capital F required to pull the coin over the step. Make a vatte full karanda avashya minimum force. When you apply minimum force, let's assume this just starts to shift. No circular motions. It's going to rotate around which point? Around this point. Right? So always it is going to have a reaction. Right? This point is in contact always until the coin is pulled up completely, until the coin is completely pulled up. Always this point O is going to be in contact with the coin, which means there's going to be a reaction always acting to the center. Center එක දිශාවට හැම වෙලෙම reaction එකක් තියෙනවා. Right? Just find this F. Find this F. The minimum force. Minimum force is when it starts to break the equilibrium. Equilibrium එක කැඩෙන මොහොත. හරි? දැන් ඔයාලට එහෙම ලොකු දඩ force එකක් දුන්නා මේක සෙනික කැරකිලා එනවනේ. That's not the instance they are asking you to find. They're asking you to find the minimum force. The minimum force means the point where the equilibrium just breaks. The instance is what? The equilibrium just breaks. Equilibrium just breaks means this loses contact. This loses contact. Right? Equilibrium just breaks means still we can assume equilibrium. Equilibrium කැඩෙන ඔන්න මෙන්න මොහොත කියන්නේ you can consider it still is in equilibrium as well.
Yeah.
Equilibrium as well.
Yeah.
You know, right? So that limiting state, at the limiting state, you can assume that it is still in equilibrium for the theoretical purpose. Right. Now, if they want to find it, you would have to maybe apply a moment around the point 2. What if we apply moment around the point 2? Point 2 is what a moment that comes.
S
So
cancel.
you apply mg into
R.
mg into r.
R
and
into equals R into
f into
R.
r. Right? So the answer is going to be f min is mg. Right? You just have to apply a minimum force mg in order to shift these up. Minimum. That's the minimum. Where the equilibrium just breaks. Where the equilibrium just breaks. Was it clear? The 23, 2007, it's an easy question, but just see whether you could figure it out.
Okay.
Okay, let's see. The same figure ABCD shows 4 ways in which a light spring balance can be loaded with a weight 100 newtons using a frictionless pulley. We need to find the scale readings of the spring balances in the 4 cases. We have to see the scale readings. So if you see,
First one is definitely 100.
okay, that's 100%, 100, right? So like, yeah. So this is tension. This is going to be the tension. So that is going to be 100.
The last one was 100.
Yeah, this is 100 as well as saying. Okay, let us see. Again, let's assume this is the top. This is the top. This is the point where the reading is shown, right? So therefore, it doesn't matter whatever what's the mass connected to this side, right? Because to that hook, what's connected is this mass. So therefore, it's going to stretch based on this mass. So this doesn't matter, right? Therefore, what's the tension I can break it below it? T. It's once again 100. Tension is 100 since it's in equilibrium. So therefore, it's going to read as 100 as well. So let us come to this. This is also 100, right? Because tension is going to be 100.
Yes, sir.
This reads 100. It's 100. So here, tension is going to be 100. So tension, does it matter?
No, it's cos.
No. Right? The tension, like, okay, see, what's the tension? Tension is 100. Tension of this is 100.
Yeah.
Right? Now, if you see, it's throughout the system, it's one string. So throughout the string, the tension should be T. Throughout the string, the tension should be T. So මෙතන 100 නම් මෙතනත් 100 මෙතනත් 100 මෙතනත් 100 මේක අලගලා අල්පකින් වඩා
Is it, sir? Okay.
right? It makes it no. Everything reads 100. So the answer is
One.
One. Yeah, right. So fine, that is okay. Let's go as the final question. Let's go for the 2013 question. Let's go for that's as the final question. 2013. Right. It says a man of mass 60 kilograms standing on a uniform wooden rafter hung horizontally by two identical ropes is painting a wall, right? The mass of the rafter is 20 kilograms. What is the minimum tension? What's the minimum tension that should be withheld by each rope so that the man can move safely? Okay, so they're asking the minimum tension that the string should have in order for this man to move safely from A to B. Now, think about what kind of an approach you would have to do in order to solve this question. This is a good question. So let us first of all, this is an equilibrium question. So therefore, let us first of all mark all the possible forces acting on the system, right? So let's do that. It's going to be TA, TB. The total mass of the rafter is going to be 20 kg, which means 200 newtons. This guy is going to have 600 newtons. So what they're asking is, what should be the minimum tension that each of these strings should contain in order for the man to safely travel across A and B? Minimum tension. Right. This is how you find it.
Is it 100?
How did you come with 100?
Because it's no, I don't.
You need to have a proper plan, right? So this is a good question, right? So therefore, like, listen well. So now think, first of all, let us find what's the minimum tension that A should have. Let's assume what's the minimum tension that A should have. ඒගේ ටෙන්ෂන් එක වැඩිම වෙන්නේ ඒගේ ටෙන්ෂන් එක වැඩිම වෙන්නේ when the man is at A, right? When the man is at A, the tension in A is the
Highest.
maximum. When the man is at the point B, the tension of
TB
B
is
is
the
maximum.
maximum.
Yeah.
Right? Somehow, therefore, like, we need to have the tensions of these strings, the maximum. යාලට තියෙන්න අවශ්‍ය ඒ maximum අගේ තියෙන්න ඕනේ. maximum අගේ තියෙන්න ඕනේ. දැන් හිතන්නකෝ දැන් මෙයා මෙතනට ආවම මේ string එක කැඩෙන්න හොඳ නැහැ.
Yeah.
When this guy comes to this point, the string shouldn't disconnect, which means we need to put this guy here and find what's the tension TA. String එක disconnect වෙන්න නැතුව තියෙන අවශ්‍ය TA එක හොයනවා. මෙයා මෙතෙන්ට දානවා. ඊට පස්සේ we
Almost
find
done.
what's the tension that needs to be there in this string such that the string doesn't disconnect, right? So that's the minimum tension that both should have, right? So yeah, between A and B, what is the minimum tension that should be withheld by each row? Yeah. So let us put this guy somewhere here. Symmetric, right? Let's put this guy here. Let's remove this guy from here. Let's include him somewhere here, right? So then only the most dangerous situation comes, right? Because the chances of this tension to disconnect is high. So therefore, let us find the tension that this string should have such that this system is in equilibrium. Disconnect in equilibrium. මෙයා මෙතනට ගියාට පස්සේ සිස්ටම් එකේ ඉක්විලිබ්‍රියම් එකේ තියෙන්න අවශ්‍ය tension, right? So I'll find that easily by applying moment around A. A වටේ moment එකක් දාපුවම A එන්නේ නැහැ equation එකට. A is not going to be there in the equation, right? So 200 into, let's say this is L. 200 into L. This guy 600 plus 600 into 2L, right? Because this is L, this is L, 2L, and the anti-clockwise moment is given by whom? TB into TB into 2L, right? So yeah, let us find that what it is. L capuna 200 and 1200 is 1400. 2 TB, so TB is 700 newtons, right? So actually, although I mark these as TA and TB, we need to understand well that both are going to have the same tension, symmetric. It's symmetric. Yeah, මෙතනදී මෙයාට 700 නම් මෙහා පැත්තට ගියාම මේක වටේ symmetric moment එකක් දැම්මොත් ඒත් මෙයාට 700 එන්නේ, right? So when this guy is here, if you apply moment around the point A, this tension we got as 700. So let's put this guy here and apply a moment around B. Once again the same, 200 into L, 600 into 2L, TA into 2L. Once again TA is going to be 700. So each of these tensions, if they are 700 each, then the string will never disconnect. The string will never disconnect. It's safe. The most dangerous point is when the man reaches the corner. So even when the man reaches the corner, if the system is in equilibrium, then it's safe. It's safe. Clear, or else like do you have any confusions? Can you?
That's clear. That's all.
Sure. Both.
Yeah.
Understood?
Yes, that's sure. Yes.
Right. Okay. Fine. Right. Okay. That is 700. All right. So let us. I think there is few more questions. 30th, try it alone, right? I think equilibrium. Let's wind up the equilibrium part from this, right? So